All right, welcome. In this video, I'm going to be doing some examples on dimension. And I think, really working with the rank nullity theorem for linear algebra. And so the first kind of set of problems is just determine why S is not a basis for R2 or why S is not a basis for R3, which, I don't know, I feel like these may have been better suited for the previous homework, but we can work these, right? Okay, U1. Okay, U1 can't span all of R2. Okay, a set of one vector can't have dimension 2, right? Or the span of one vector, yeah, I think that's what I was saying. The span of one vector can have at most dimension 1, unless that vector was the 0 vector, in which case it would have dimension 0. Okay, so I would say for 1a, dimension of the span of S is less than or equal to 1, which is certainly less than 2, so it can't be a basis for R2. Not enough vectors is another way of saying it. U1 and U5, U5 is just 3 times U1, which means that this is a dependent set. And so I guess really in A, to say why it's not a basis in terms of the dimension of basis for R2, is that the span of S is not equal to R2. It's kind of a better response, I think. And then for C, U1, U2, and U3, well, a set of 3 two-dimensional vectors has to be linearly dependent because there's too many vectors. So oops. All right, and okay, that's it. So now why are these not a basis for R3? Well, part B on this one's going to be the same exact thing. I'm going to have 4 3-dimensional vectors, which is too many to be independent. Okay, I'm going to have dependency. Because when I'm going to check that, check it for dependency by trying to solve the equation, or trying to solve the system corresponding to how can I linearly combine V1, V2, V3, and V4 to get the 0 vector, it's going to be a homogeneous system with more variables than equations, which has to have infinitely many solutions, which means that there are non-trivial solutions, which means that the set is linearly dependent. So I'm going to start with that. 2b, S is linearly dependent is why it's not a basis for R3, and I just told you why it was linearly dependent. 2a, okay, V1 and V2, okay, they are independent. You can't see V1, V1's right there. Okay, V1 and V2 are independent. Neither of them is a multiple of the other, but they can't span R3 because their dimension of their span is going to be 2 because they're 2 linearly independent vectors, but R3 has dimension 3, so the dimension doesn't match up. So I'm going to say span of S is not equal to R3. And that's it for that one. All right, find the dimension of W when the components of each vector in W satisfy the given conditions. Okay, I think we're just going to go over here and just kind of start investigating on, okay, if I'm going to solve for x1 here. x1 equals 2x2 minus x3 plus x4, meaning that x2 can be whatever it wants, x3 can be whatever it wants, and x4 can also be whatever it wants. Okay? And that means that I've got 3 independent variables. So if I was to, and maybe I'll go through the one time to show you why the number of independent variables is going to be the same as the dimension, right? I'm going to say that I'm going to factor out an x2, and I'm left with a 2, 1, 0, 0, plus x3 times negative 1, 1, 0, and x4 times, what do I have, 1, 0, 0, 1. Okay, and that means that, this whole space can be expressed as the span of these 3 vectors, which are linearly independent, meaning these three vectors form a basis for space W that fits this constraint, meaning the dimension of W is 3. And for that reason, for the rest of these, I'm going to just be finding the number of independent variables and saying that that's going to be the dimension, because I could go through that process and say, okay, you know, basis for W equals this and that, and the third one, that's a basis. It's got 3 elements in it. That means the dimension's 3. Okay. Part B, I've got 1 equation, but I'm still in R4. Remember that. That's the, I think there was one like this in the last problem set, and that was a discussion we had in class. Was that, you know, you got to, okay, we're going to solve for x1, kind of like normal. Okay, but remember that there's also an x2, x3 also, and x4. Okay, just because we didn't say anything about x2 and x4, well, I guess that really means they can be whatever they want, because we are still as a subspace of R4. So I've got 2, 3, and 4. That's 3 independent variables. So I'm going to say that the dimension of W is equal to 3 again. Hey, you might be starting to put together something about the, you know, the size of the space it's contained in and the number of constraining equations, right? These both had one equation, dimension 3. But, you know, you want to keep investigating, make sure that holds in general. All right. So for part C, which I could just scoot that up there. Part C, what's going to happen is I've got x1 and x3 dependent on x2 and x4. So x2 and x4 are independent. And I guess I should probably say they're independent variables. I'm talking about linear independent there. x2 and x4 are my independent variables. So I'm going to conclude that the dimension of W is equal to 2. Okay. Over here, the only free variable I have is x4. So I'm going to conclude that, you know, the dimension of W is equal to 1. Okay. Now we're going to find a basis for the null space of the matrix and then give the rank and nullity of that matrix based on that. And that'll be good. Okay, the basis for the null space will give us the nullity, right? We'll just count the number of vectors in the basis for the null space, and that'll be the nullity. The rank will be something we'll use the rank nullity theorem to determine, right? So I'm going to start by row reducing this thing. And clear out the first column by subtracting 2 of row 1 from row 2. So subtracting -2 is going to give me a 1 there. 8 minus 6 is 2. Okay, so I'm still with -1 and 3 there. And then I'm going to add row 1 to row 3. And I'll have 0, 3, 6. Okay, that's promising. I'll have at least something interesting. But I guess it is not interesting, or not. It's not uninteresting to investigate a non-singular matrix. We should probably do that at least once, and if I don't have it on this problem set, then I'll make sure to do one in class or something like that, and just point out that that is also definitely a possibility. It's pretty easy, but okay. Wait, no. Hold on. Then I'm going to subtract 3 copies of row 1 or row 2 from row. And so I will get my row of all zeros, and then I'm going to add back up there to kill off that 1. So I'm going to have 1, 0, 0, 0, 1, 0. And then when I add there, I'll have 5, 2, and 0. All right. So I've got my fully reduced matrix. And then I'm going to say, all right, this is telling me that if I was to augment this with the 0 vector to find out where the solutions to ax equals 0, I'd have x1 plus 5x3 equals 0, and x2 plus 2x3 equals 0. Okay, that tells me that x1 equals -5x3, and x2 equals -2x3, and x3 can be whatever it wants. Okay, so the basis for because all of the vectors in the null space are a multiple of the vector -5, -2, 1, right? That multiple is x3. Whatever you want x3 to be, that's going to be the multiple of that vector. So it's going to have dimension 1, because it only has one free variable. But I'm going to say that the basis for the null space of A is going to be the set of with the vector -5, -2, 1 in it. Okay, that means that the nullity of A is 1 because there's one vector in the null space. I mean, in the basis for the null space. And the rank of A is equal to, well, it's the number of columns minus the nullity. So it's going to be 3 columns minus the nullity is 1, which is 2. Okay, that's the rank nullity theorem. Is that the rank plus the nullity has to add up to be the number of columns of your matrix. All right, that was part A. Okay. We know part B is going to have an interesting null space because it's a wide matrix, and all wide matrices have non-trivial null spaces. Okay. And so I'm going to start in, I'm still in the shot. Start by row reducing, clearing out the first column. Just like always, I'm going to have one copy of row 1 subtracted from row 2, so 3 minus 2 is 1. 1 minus 0, also 1. 7 minus 5 is 2. All right, then I'm going to subtract 2 copies of row 1 from row 3, and I'm going to have 3 minus 4 is -1. -1 minus 0 is -1, and I bet this is going to come back -2, right? So 9 minus 10. I'm missing something? Oh, no, I see. It's that those are going to... Okay. Anyway, let me just double check that. 9 minus 10 is indeed -1. Okay, that's cool. Okay, this one's going to take a couple more steps. So now I'm going to use this to clear out the rest of its column. So I'm going to subtract 2 copies of row 2 from row 1. So 2 minus 2 is 0. 0 minus 2 is -2. 5 minus 4 is 1. I still have 1, 1, 2. And then I'm going to add these down. So I'm going to get 0 and 0. And, hold on, what was I thinking here? Oh, I was just adding. So 2 minus 1 is 1. Okay, and I think that this is almost in fully reduced form, right? At this point, I've got 3 pivots. I'm not going to be able to get a 4th, right? I'm restricted by my number of rows, really. But now what I'm going to do is I know I'm going to use this to clear out the rest of that column. So I'm just going to kind of do that real quick. And just put in some zeros there. And then I'll have myself... There we go. I've got myself a fully reduced matrix. Okay, what this is saying is that for the null space, I need to slide this over a little bit. For the null space, x1 minus 2x3 is equal to, so I'm going to say x1 equals 2x3. x2 plus x3 equals 0, so x2 and x is the negative of x3. And this is saying that x4 needs to equal 0. Okay. So what this is, could say that, the different way of writing this is that the null space of A is equal to the set of all vectors x in R4 for which x equals, I'm going to factor out the x3. x3 can be whatever it wants. I didn't really write that in there, but that's the independent variable right in there. x3 times 2, -1. x3 is 1, and 0 because x4 has to be 0. So it's the set of all multiples of this vector. So this vector spans the null space. And the set that has it has just that vector in it, 2, -1, 1, 0. That will be a basis for the null space because it's an independent set. So that means that the nullity of A is equal to 1 because there's only one vector in the basis. And therefore the rank of A is equal to the number of columns minus the nullity, which is going to be 3. Right. So this problem is going to be very similar in that we're going to row reduce it. We're going to find the rank by identifying the number of pivots. Okay. Oh, actually, no. We're going to find a basis for the range by using probably range trick 1. In my class, we call it range trick 1, where we identify the pivots, backtrack those to the columns of the original matrix that induced the pivots, and those columns form a basis for the range. Oh, hold on. Stuff falling. All right, that's better. So, basis for the range of A, I'm just going to start row reducing. This is not a matrix that I have row reduced elsewhere in this problem set, so I'm just going to do it fresh. 1, 0, 0. I'm adding, subtracting. 7 minus 1 is 6. 3 plus 1 is 4. Okay, that's a good sign. I know I'm getting what I'm supposed to. 1, 2, 1, and then, okay. I'm going to probably divide this by 2 while using it to clear out this row because, you know, this row is just 1.5 times the second row. So I'm going to have 1, 0, 0. This is going to be a row of all zeros. I'll have 1, 2, and then when I subtract, really I'm just going to subtract row 2 from row 1 right here, 2 minus 2 and 1 minus 4. And I've got a fully reduced matrix. So this is x1 equals 3x3, x2 equals negative 2x3, x3 can be what it likes. Pardon me, I was doing the null space again. Just ignore that. All right. Yes, identify the pivots. Here they are. They're happening in columns 1 and 2. So columns 1 and 2 of the original matrix will form a basis for the range. Basis for the range of A is going to be, but what I was showing over here, you can see that there's going to be one independent variable in the null space, so the nullity is going to be 1, but let's see that a different way, right? So a basis is going to be 1, negative 1, 1, and 2, 0, 5. All right. That means that the rank of A is equal to 2, right? Because there's 2 vectors in the basis for the range. And then the nullity is equal to the number of columns minus the rank, which is going to be 1. Okay. Let's have room on this page for one more problem. Part B. All right. Hopefully, let's get you going. 1, 0, 0. So I'm going to subtract 2 copies of row 1 from both row 2 and row 3. So 4 minus 2 is 2. 1 minus 2. 1 minus 2 ones. Yeah, it's going to be negative 1. Okay, subtracting 2 row 1s from row 2, that'll be negative 2. Subtracting 4 is going to be 1. Okay, I'm going to have some cancellation there. And this column will remain unchanged if I'm subtracting row 1 from, you know, any number of copies of row 1 from row 2 and row 3, because that's a 0. So that'll be 4 and negative 2. And that's a 1, 2, 0. All right. Now, I think really I'm going to divide this all out, or divide the 2 out. So I'll have a 1, negative 1, 2. Add that down to kill off the whole third row. So 1, 1, 2, 0. 0, 1, negative 1, 2. 0, 0, 0, 0. Okay, this is not fully reduced because not each leading 1 is the only non-zero entry in its column. So I'm going to need to subtract up there. Although you can probably see where this is headed, right? Like you know what it's going to be, but you know that's going to be a pivot. I'm not going to have any other pivots besides this one and that one. So you know the range is going to be 2. But if we're trying to exhibit a basis for the range, then we want it in fully reduced form, right? So we're going to subtract 1 copy of row 2 from row 1. Okay, now I've got a fully reduced matrix. Okay, that highlighter didn't look great last time, so maybe I'll just use a red pen and I'll say that these are my pivots. So these are my 2 independent vectors. Now, if you had row reduced this a different way, it wouldn't be in reduced echelon form where, we're cascading down and attacking left to right. But you could have found a different pair of 2 vectors that were independent and spanned the range. But for me, I'm just going to use the first 2. And range of A equals, really, it's the span of 1, 2, 2 and 1, 4, 1. I don't know what I was doing there because I was just supposed to write a basis, but, let's say these are pretty clearly independent because they're not a multiple of each other, and there's only 2 of them. They span their span, okay, which is the range. And so this is going to form a basis, and maybe I just scratch that out and I turn that into some curly braces, and then I say that's a basis for the range of A. And since there's 2 vectors in the basis, I've got, let's see, rank 2. Since there was 4 columns, I'm going to say the nullity of A is equal to the number of columns minus the rank, which is going to be 2. All right. What does subspace defined by W equals span of S? Find a basis for W and calculate its dimension. That's number 6. So what I'm going to do for this one, I'm going to just kind of do range trick number 1 on this set. I'm going to row reduce. I'm going to turn it into a matrix to basically find the solutions, to find the ways that I can linearly combine these and get the 0 vector, which I know there's going to be non-trivial ways because there's 4 3-dimensional vectors, right? So I can always solve for one in terms of the others. Let's say so I'm going to row reduce this. Let's see, wait, I have not. I'm just making sure I don't have this matrix elsewhere and I didn't already do this row reduction. I don't think I have. So row 2 minus row 1, row 3 plus 2 row 1s. So I'm not going to be changing the first row in this step. I'm going to be subtracting. So negative 2 minus negative 1 is negative 1. 0 minus 1 is negative 1. Negative 1 minus 2 is negative 3. If I'm adding 2, adding negative 2, adding 2, adding 2 2's, so I'm adding 4 to 0, and that's going to be 4. All right. Now I'm going to see, I'm going to make these all positive. Add that there, subtract it from here. 1. Okay, I'm adding row 2 to row 3, so that's going to be a 2, and that's going to be 5. Okay, 0, 1, 1, 3. And then I'm going to subtract here, so I'm going to have 0, 0, 0. 4 minus 3 is 1. Then I'm going to use this to clear out the rest of that column. So I have 1, 0, 0, 0, 1, 0, 2, 1, 0, and 0, 0, 1. Okay. meaning my pivots are here and in the fourth column. So my three independent vectors are vector 1, vector 2, and vector 4. Okay, a basis for W is going to be that independent set that still spans the same as, has the same span as original S. So the basis for the span of S is going to be the set that has vectors vector 1, vector 2, and vector 4. That's 2, negative 1, 0. Oh, and then the dimension of the span of S, or the dimension of W, which is the span of S, is going to be 3 because there's 3 vectors in the basis. All right, determine the largest possible rank value of the rank of A and the smallest possible value for the nullity of A, which I think might be the same thing. I put this problem on here. I don't think I've used this problem before, and I thought it was interesting, but I don't think I've really thought through it yet. I just kind of made the problem set, assigned it, and here I am a couple days later working the problems. Once you all need solutions. Okay, so if A is 3 by 3, the largest possible rank is 3, right? If it's a square matrix and it's non-singular, it'll have full rank. And so, oh, okay, the smallest possible for the value of the nullity of A follows directly from the largest possible value of the rank of A. And they're not going to necessarily be the same thing because of the complementary nature. I think you'll see what I'm saying. Okay. If A, which is a 3 by 3 matrix, if it's non-singular, then I've got a situation where the rank is 3. And in that case, the nullity of A would be 0. All right. If A is 3 by 4, okay, the number of pivots is kind of has an upper bound of the minimum of the number of rows and columns of a matrix, and I think that's something we've noticed in this class so far. So in a 3 by 4 case, I can have no more than 3 pivots, okay, meaning the rank is going to be capped at 3. Oh, whoops. Yeah. So the maximum possible value of the is equal to the minimum of 3 and 4. Okay. Because it's a 3 by 4 matrix, which is, okay, the minimum of 3 and 4 is 3. Okay, so what I'm thinking is that, okay, the maximum value of rank of A is 3, therefore the minimum value of the nullity of A is going to be where I'm taking the number of columns, which is 4, minus the maximum amount of rank, right? Subtract the most you can to get the minimum nullity, and that's going to be 1. And we already know that a wide matrix has nullity greater than 0, I guess what I would say. Okay, so I'm starting to see what this problem's getting at. Okay, so A is a 5 by 4 matrix, so the maximum rank for is going to be the minimum of 5 and 4, which is going to be 4. And then the minimum nullity is equal to the number of columns minus the maximum rank, and that'll be 0. Okay. Okay, now number 8. This one I assigned, and I wasn't really sure if y'all knew how to prove something like this, but I figured throw it out there, see what you know. Okay, suppose A is a non-singular matrix. Suppose B is an m by n matrix. Okay? So basically so that the product AB is well defined. Okay? And we're going to prove that the null space of AB is equal to the null space of B. Now the null spaces are sets. And if you want to show that two sets are equal, I don't think I've talked about this with y'all, But if you want to show that two sets are equal, you have to show mutual containment. Okay, so we have to show that the null space of A, of the product AB, lives inside of the null space of B, and then we will show that the null space of B is contained in the null space of AB. And, well, I'm not sure how hard that's going to be. Find out. Have not practiced this one before recording the video. So we'll see. Okay. So first step, show that which one do I want to do first? I think that the null space of B is contained within the null space of A times B. Okay, so how we do that is we say, suppose vector x is in the null space of B. And then we're going to show that it's in the null space of AB. Okay, that means that bx equals the 0 vector. That's what it means to be in the null space. Okay, now we want to figure out what is, I know how this is going to go. This is not going to be hard. We want to find out what happens when I take AB and multiply it by x. Because if I get 0 back, then that means that x is in the null space of AB, right? So let's just say, well, I know that matrix multiplication, just so long as it exists, it associates. So it does not commute. So I'm going to say that's A times bx, and that's equal to A times the 0 vector, which is the 0 vector. Okay? Which means that x is in the null space of AB, which means that, hold on. I'm thinking about the other direction already, and I'm a little stuck on where I'm going to show that. But okay, if x is in the null space of AB, and x is any vector in the null space of B, I have shown that the entirety of the null space of B is contained within the null space of A times B. Okay? So that's the first half. The second half, okay, is going to be null space of AB lives in null space of B. That's, I feel like, going to be a little trickier. Because how do I get rid of it? Okay, I mean, we haven't really proved in class that all non-singular matrices are invertible, but I think we all know it. And I think I might be having to use that fact. I can't really see anything else. It's like, look at my computer screen, I can look on the piece of paper I'm writing on. I'm not really seeing anything else besides kind of like solving at it. And maybe I'll pause for a second. Okay, no, I'm good. I don't think I needed to put pencil to paper and see. I just kind of scratched it off to the side, and very quickly the conclusion just fell out. So what I want to do is suppose x is in the null space of A times B. It's pretty much the opposite of what I did over here. All right, and then I'm going to say that means to me that matrix AB multiplied by x is equal to the 0 vector. But again, I know that matrix multiplication associates if it's defined. So I've got A times bx equals 0. Okay? But from the statement of the question, A is a non-singular matrix. Okay, so if A is non-singular, the only way I can take A and multiply it by a vector, and B times x is going to be a vector. Okay, the only way I can take A and multiply it by a vector and get 0 back is for that vector to be 0. So that means that bx is equal to 0. And if bx equals 0, then that means that x is in the null space of B. Okay. And yeah, I'm really glad I put that problem on the homework, because this is definitely at your level. It's very understandable, and I don't want to, send you off to the next place without being able to show that two sets are equal by showing mutual containment. I'm glad that showed up. Okay, and that's all the examples I've got for dimension, and yeah, I think that's going to be enough for this video. So thanks for watching.